Let's talk chemistry with Pastor Dan. We're continuing to look at the atom. The atom is the smallest part of an element that still retains the properties of that element, same we discussed it yesterday. In order to get some values out of it, we have a couple of values we have to look at. The first is called atomic mass. Now, there's an old number system called A. Many teachers don't use it anymore. A is the atomic mass. It's the mass of a nucleus, number of protons, and number of neutrons. Also, there's atomic number, old system Z, just the number of protons. Now, we don't express these in grams or liters or anything like that. Instead, we use a value called AMUs. AMU stands for atomic mass units. Chemists genuinely are a lazy bunch. So instead of writing AMUs, we just write U's. U represent atomic mass units. Now, let's do a little practice here. Let's say we take potassium. Potassium is symbolized by the letter K, has atomic mass of 39, atomic number 19. Since atomic number is number of protons, I have 19 protons. Now, the charge of a neutral element, being neutral, has no charge. So I have 19 positives. I also have to have 19 negatives. Now, to find the number of neutrons, then we take the atomic mass, number of protons and neutrons, subtract from the number of protons, 39 minus 19, we get 20. Now do these three also on your own. So pause it a second here and go through and see if you come up with them. Hopefully you did that. Here's the answers. All right, so we should have 3, 4, and 3 for lithium, 10, 10, and 10 for neon, and 71, 104, and 71 for luteum. All right, hopefully that wasn't too bad. Now, there are two values that we're going to look at here. It's called abundance. Now, abundance is the means of determining the mass of an atom based on the average of all the isotopes. What's an isotope? An isotope is an element with the same number of protons, but a different number of neutrons. So let's take an example. Let's make sure we take a picture here first. Looking at the atomic masses, you see these numbers aren't whole numbers. The reason why these numbers aren't whole numbers is because this is the average of all the isotopes that exist. So if we look at iron, most of it's going to be around 56, but we do have some that's a little lower, a little higher. That's the way this works. So let's take an example of carbon. There's at least two isotopes of carbon, carbon 14 and carbon 12. If I look at that, I have 6 protons, 8 neutrons, and 6 electrons for carbon 14. We have 6, 6, and 6 for carbon 12. Now, carbon 14 is used in something called carbon dating. Carbon dating is not overly an accurate system beyond 10,000 years. We talk about radioactivity. We'll talk about that a little later. All right, so let's take a look at a problem. An element with a discovered named kelenite. A former teacher I worked with named Mr. Kelly. So there is the element named after him. There's 3 isotopes here. Atomic mass 220 with the 55.95% of it. We have 221 with 21.98% of it, and 212 atomic mass with percentage of 22.07. So how do we do this? Well, we're going to take the first isotope and multiply the decimal percentage of that, and do the rest likewise for however many isotopes we have of that element. So in this example, we're going to start with, and that's going to equal my value A, my atomic mass. So we're going to start with 220. That's my first isotope there. And there's 55.95%. As a decimal, that's going to be 0.5595. We do the same with the other values. So 221 times 0.2198 and 212 times 0.2207. Now this number here, 222, is an exact number. I cannot get 220.1. I can't get 219.9 used. Since it's exactly, that's infinitely significant. We're going to sig figs only from the percentages. So in this case, 220 times 0.5595, it's coming to 4 sig figs. Do the math on your calculator. You should get 123.1 U. Now do the other two as well. When you do, you should get 48.58 U and 46.79 U. When we add those all together, we get 218.5 U. And remember the last filled column for addition, so it goes to 10th place. That would be the atomic mass. That's how we record it for this element. Make sure that we show the process through, make sure we follow sig figs. Now we can also go this process in the opposite direction. Now we can do multiple but then you're getting into matrices and calculus. So we're going to keep it simple for Chem 1. So we're only use 2 isotopes. So let's say there's chlorine. Chlorine atomic mass, it says only 2 that exist, 35 and 36. So we take our first atomic mass, 35, and we don't know the average, the percentage. So we're just going to make it X. And then we're going to add to it 36. Why is it 1 minus X? Well, 1 is 100%. As a decimal, that would be 1. 100% minus whatever the other one, 1 minus X. And that's going to equal the atomic mass from the periodic chart I found, 35.453. So we're going to do a little algebra here, multiply through. So we're going to get 35X plus 36 minus 36X is equal to 35.453. Combine like terms. We get 36 minus X is equal to 35.453. We're going to subtract 36 on both sides. When I do, I get minus X is minus 0.547, and then divide both sides by minus 1. So X is going to be 0.547. Again, I want percentage, so 35 is going to be 54.7%. To find them out the 36, that was 1 minus X, remember. So 1 minus 0.547 gives us 0.453. So the amount of that 36 is 45.3%. We're going to do a couple more of those. So let's do this one. Former principal I worked with, his name is Mr. Wolfarth. So we're going to work Wolfarthium. So here we go for this process. We're going to take 300 times 0.3355. And then we'll take the other two values, 302 times 0.4145 and 305 times 0.2500. Multiplying through, we get 100.7. Following stick figure rules, only have 4 there. We have 125.2 and 76.25. Now, just so you know, this is a check. The number should fall between 300 and 305. If it does not, you've done something wrong. So when we add these up, we get 302, which does fall inside that range. So 302.2 is my atomic mass. There we go. Let's try one more the opposite way this time. Let's do carbon 14. So let's say there's only those 2 isotopes. So we take 12X plus 14 times 1 minus X. That's equal to 12.011. Multiplying through, we got 12X plus 14 minus 14X is 12.011. Common factors, I have 14X and minus 14X. It's going to get 14 minus 2X is 12.011. Let's get rid of that 14, move it to the other side, subtract both sides by 14. I get minus 2 is equal to negative 1.989. Divide both sides by negative 2 to get X by itself. X is equal to 0.9945. So when we do that, the amount that 12 is 99.45%. Moving it 2 places to the right to make a percentage. To find the amount, that's 1 minus X. 1 minus 0.9945 is going to be 0.0055. So 14 is 0.55%. There we go. Those are our answers. All right. I'm going to have you do 2 now on your own. So do these on your own. A former administrator also named Howick. So it's Howickium. There is the percentages. One thing I want you to be aware of, this 3.67. People have a tendency to make that 0.3635. It's going to be 0.036 because they go 2 decimal places to make it a decimal. And then I want you to find the amount that is iron 56 and iron 52. And the atomic mass there is 56.0. Let's take a look back. Where is it at? Right back to there. So iron 56.845. I hope that's what I used over here before. We'll see. There we go. So 8.845. Do the math on your own. See what you come up with. And I'm going to show you the answers here. They are, so 289.65U is my answer for the first one. And we have 96.13% for 56 and 3.87% for 52. Hopefully this wasn't too bad. Take care. Be good. God bless. Bye.